All right. Good evening. Welcome, everyone. Welcome back to Mr. Isaac's math class. If you have not subscribed to this channel, I encourage you to do so that you can always be informed whenever I post more videos. Now, look at your screen and do you remember these numbers on your screen? In one of our previous videos, we introduced this beautiful set of numbers, and the list goes on. We introduced this beautiful set of numbers 2, 3, 5, 7, 11, 13, 17, 23. You remember this list? 29, 31. The list continues. We call them a very special name. We said they are called prime numbers. Now, we talked about prime numbers and we also talked about prime factors in our previous videos. If you have not watched those, I advise you do watch them so that you will understand everything we're going to be saying in this video. And what we're going to do today is to take just one step further to talk about prime factorization. Now, what do we mean when we talk about prime factorization? By prime factorization, we want to express every given number as a product of only its prime factors. What we mean by that is we want to pick any kind of number and write that number as a product of only prime numbers. That is, we want to find what kind of prime numbers can we multiply so that the answer is that number in question. That is what we're looking at. So what we're going to do today is it doesn't matter what number we take. What we're interested in is that we only want to multiply prime numbers together so that it can get us that number. All right. So that is that is what we're going to be doing this evening. And the first number we're going to pick, let's pick the number 40. So let's take some examples under this. So we're going to express 40 as a product of its prime factors. That is what we are going to do. Let's begin with 40 and we will proceed. Now, how do we do that? Now, remember we talked about tests of divisibility. We're going to make use of tests of divisibility here to accomplish that task. So the number we are considering is the number 40. So we're going to place it like this. So we place 40 here. We place 40 here. Now look at the prime numbers. We want to express 40 as a product of its prime factors. So look at the prime numbers that we have placed there. Which of these prime numbers can divide 40 exactly? Let's begin with 2. We ask the question, can 2 divide 40 exactly without a remainder? Pause for a while and think, can 2 divide 40? Yes. From our video on tests of divisibility, you know that 2 can divide 40 exactly without a remainder because 40 is an even number, right? So let's place 2 there. Now, how many times can 2 divide 40? Like, how many 2's can we find in 40? Well, let's do that digit by digit. 2 inside 4. How many 2's can we get inside 4? We can get 2 2's inside 4. There's no remainder. Okay, what about 0? How many 2 can we get in 0? We can get no 2 in 0. That's 0. All right, that means 2 can divide 40 exactly to give us 20. All right, let's check again. Can 2 still divide 20? Sure, 2 can, since 20 is an even number. Because 2 can divide every even number. So sure, 2 can divide 20. All right, so let's pick 2. Say 2 into 20. 2 into 2 is 1. 2 into 0 is 0. Oh, 2 can divide 20 10 times. Now, can 2 still divide 10? Yes, 2 can divide, and you keep dividing the number as long as it can divide. If it's only 2 that can divide the number, fine. There's no problem with that. As long as 2 can still divide that number, keep using 2. So 2 into 10, that is 5. All right. Now, can 2 divide 5 exactly without a remainder? No way. We know that 2 cannot divide 5 because 5 is not an even number. All right. Now, since 2 can no longer divide, we move to the next prime number. And the next prime number is 3. We ask the question, can 3 divide 5 exactly without a remainder? No way. 3 cannot divide 5. Oh, that means we can use 3. Let's move to 5. Can 5 divide itself without a remainder? Yes. 5 can divide itself one time. So 5 into 5, one time. And that is the end of our division. So once we get one, we're going to stop. All right. We're going to stop there. So this means, what this means is this. This means that this implies that this implies that we can write 40 as 2 times 2 times 2 times 5. What have we done here? We have ended up expressing 40 as just some prime numbers multiplying themselves. The first number here is a prime number, the second is a prime number, the third is a prime number, the last is a prime number. And all these numbers multiply together to give 40. Because 2 times 2 is 4, 4 times 2 is 8, and 8 times 5 is 40. That's all about prime factorization. We want to just express 40 in such a way that it's only some prime numbers multiplying themselves to give us 40. So we're going to go ahead and pick another example. Let's take example 2. Example 2. Let's think about 48. So example 2 says express 48 as a product. This is example 2, as a product of its prime factors. Remember our prime numbers, 2, 3, we are still picking from this list. Every number we are picking must come from this list, 2, 3, 5, 7, 11, 13, 17, 23, like that. We cannot go and pick any number outside of this list because what we want to do is to express the given number, whatever number we are given, is to write it as some prime numbers multiplying themselves. So now we are given the number 40. We're still going to do the same thing that we did. We have given the number 48, and we're going to do the same thing as we did for 40. So let's go back to our list of prime numbers. The first prime number here is 2. So the question we're asking is this: can 2 divide 48? That is, can 2 go into 48 exactly without a remainder? And sure, we know that that can happen because 48 is an even number. This was why we needed to take the test of divisibility, because the test of divisibility will help us to know whether or not a certain number is divisible by another. So 2 can divide 48 exactly because 48 is an even number. And look at that. Let's do it digit by digit. We say 2 into 4, we get 2. 2 into 8, we get 4. All right, that's great. That means 2 can divide 48 exactly. Can 2 still divide 24? Sure, 2 can still divide 24. So let's say 2 into 24. This gives us 2 into 1 into 2 is 1, 2 into 4 is 2. That's great. We get 12. Now, can 2 still divide 12? Think about that. Can 2 divide 12? Yes, 2 can divide 12 because 12 is an even number and 2 can divide it. All right, so 2 into 12 is 6. Of course, we know 2 can still divide 6. You still use 2 into 6. That is 3. And then can 2 go into 3? No way. There will be a remainder. So we are done with 2. 2 has done its job. Let's jump over to the next prime number, whether it can help us do the next job, that which is 3. Can 3 divide 3? Yes. 3 can divide 3 without a remainder. So we say 3 into 3 is 1. Once we get 1, we stop. All right. Once we get 1, we stop. So we say this implies that 48 can be written as 2 multiplied by 2 multiplied by 2 multiplied by 2 in 4 places multiplied by 3. And very interesting, if we decide to multiply this, we are going to get 48, because 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 in 3 places is exactly 48. This is beautiful. What is the most important thing here is the fact that if you look at this product we have right here, look at this product here. Every number inside this product is a prime number. That is why it is called prime factorization. We want to factor out, we want to just write the number as some factors of the number, but these factors must be prime numbers. This is what we call prime factorization. And in the coming days, you're going to be seeing how prime factorization can be of very serious use to us. We're going to be using it to do a whole lot of beautiful stuff in maths. Okay, so finally we take just one more, and we are done for the day. Just one more. We are going to go over to 81. 81. We want to express 81 as a product of its prime factors. 81. Again, remember this. We will do this. Very important. All right, go back to our list of prime numbers. We have 2, 3, 5, 7, 11, 13, 17, 23. Let's start with 2. Can 2 divide 81? Can 2 divide 81? No way. 2 cannot divide 81. 81 is not an even number. Remember, we talked about even numbers. Since 81 is not an even number, 2 cannot divide 81. It's not possible. Okay, since 2 cannot divide, let's go to 3. Can 3 divide 81? Remember the test of divisibility for 3. How do we know whether or not a number is divisible by 3? We try to add the digits of that number. So here we add 8 to 1. That gives us 9. 9 is a multiple of 3. Actually, 3 threes is what makes 9. Therefore, 81 is divisible by 3. So let's start with 3. Okay. So how many 3's can we get inside 8? Can get 2 3's. And there's a remainder of 2. We carry it over to this side, we get 21. All right, carry 2 tens over plus 1 unit, that's 21 units. 3 into 21, that is 7. Great. Okay, now let's check again. Can 3 still divide 27? We must check for 3 before we move on. All right, we must have to check again. Get 3 going to 27. Again, check, do the test of divisibility for 3, and you're going to find that out. Let's add the digits. 2 plus 3, 2 plus 7, that is 9. It's still 9. It means 27 is divisible by 3. So we divide that 3 into 27. That gives us 9. Of course, we know that 3 can still divide 9. That gives us 3. And 3 into 3, that gives us 1. This is great. It means that we can write 81 as 3 times 3 times 3 times 3. So we're able to express 81 as a product of its prime factors. So this is what we call prime factorization. Again, if you look at this, product here, you will discover that everything here is a prime number. Actually, it is 3 repeated in 4 places. So that is the whole idea about prime factorization. We want to see how we can express every number as a product of its prime factors. And like I said, this is very beautiful. In the coming days, I'm going to be teaching you why we needed to do this. Of what importance is this? We see that it finds its importance is very, very much. What you're going to do for me now is that I'm going to give you some numbers and you will express them as a product of their prime factors, and you will put the answer for me in the comment section. Okay, so look at this. Express each of the following as a product of their prime factors. So we have 64, we have 100, we have 65. So do this and we'll meet in the comment section. Thank you very much. Have a nice day. Bye-bye.